Hi, welcome to this season's fourth episode of Schwegman, Lundberg, and Woosner's Chemistry and Biology Chemistry series. I am Nicholas Lanzatella, your moderator for the series. During this series, attorneys from the SLW law firm having a background in chemistry or biology will present on various topics at the intersection of chemical or biological sciences and patent law. We will aim to give these presentations on the second Tuesday of each month. If you attend three or more of these presentations live and you live in the US or have a mailing address in the US, we will send you a free gift. Slides for today's presentation will be available in the chat, and also a link will be emailed to you. As a reminder, nothing in today's presentation should be regarded as legal advice. If you are seeking legal advice, please consult your legal counsel. Our speaker today is Janal Kalis. Janal is a principal and registered patent attorney with expertise in chemical engineering, chemical and mechanical patent law, including over 30 years of experience drafting and prosecuting patents for chemical engineering processes, food products, cosmetics, coatings, and medical devices throughout the world. Janal received a bachelor's degree in biochemistry from the University of Minnesota, as well as a bachelor's degree in chemical engineering from the University of Minnesota. She received her law degree from the University of Utah. Prior to entering law school, Janal worked for many years as a research scientist in the area of virology and as a chemical engineer in the electrical utility industry. Janal has significant experience in counseling clients on the development and enforcement of their intellectual property portfolios. She also has experience in the preparation and negotiation of contracts for technology licensing and joint development. Today's presentation is entitled Nuclear Batteries, Past, Present, and Future. If you have any questions, please put these in the Q&A. If you look at the bottom of your Zoom window, there's a Q&A button you can press. Insert your questions there, and Janal will answer these during or after the presentation. Happy to introduce Janal. Take it away, Janal.
Thank you, Nicholas. The impetus for this webinar is actually a previous webinar that I gave on lithium-ion batteries. And one of the side subjects was nuclear batteries. I just kind of touched on it there, but afterwards I did some research. And it is an interesting area. It's not super dynamic, so we're not going to see any wowzer stuff probably, but maybe. But it is one where there's slow advancement of technology. So the first question is, what is a nuclear battery? Well, a nuclear battery is any device that harnesses energy from radioactive element isotope decay to generate electricity. Nuclear batteries do not rely upon nuclear fusion or fission. As particles are emitted from the isotope, they stir electrons in a battery system to create a current. Some batteries use radioactive decay to generate heat and then harvest with thermocouples. Others harness diode junctions to facilitate non-thermal conversion. Regardless of the method, all nuclear batteries draw energy from a radioactive source. Next slide. There are two types of nuclear batteries, thermal and non-thermal. The components of both batteries, both thermal and non-thermal, include a radioisotope fuel, radiation and heat management structures, an energy conversion transducer, and external interfaces. Next slide. The types of ionization used in modern nuclear batteries is largely alpha particles and beta particles. Now, some of the older batteries used gamma particles, and perhaps one or two companies still use that, but for the most part, it's alpha particles and beta particles. So alpha particles are positively charged and made up of 2 protons and 2 neutrons from the atom's nucleus, making them identical to the nucleus of a helium-4 atom. Alpha particles come from the decay of the heaviest radioactive elements, such as uranium, radium, and polonium. Even though alpha particles are energetic, they are so heavy that they use their energy over short distances and are unable to travel very far from the atom. The health effect from exposure to alpha particles depends greatly on how a person is exposed. Alpha particles lack the energy to penetrate even the outer layer of skin, so exposure to the outside of the body is not a major concern. Inside the body, however, they can be very harmful. If alpha emitters are inhaled, swallowed, or get into the body through a cut, alpha particles can damage sensitive living tissues. The way these large, heavy particles cause damage makes them more dangerous than other types of radiation. The ionizations they cause are very close together. They can release all their energy in a few cells. This results in more severe damage to cells and DNA. Beta particles are small, fast-moving particles with a negative electrical charge that are emitted from an atom's nucleus during radioactive decay. These particles are emitted by certain unstable atoms such as hydrogen-3 tritium, carbon-14, and strontium-90. Beta particles are more penetrating than alpha particles, but are less damaging to living tissue and DNA because the ionizations they produce are more widely spaced. They travel farther in air than alpha particles, but can be stopped by a layer of clothing or by a thin layer of substance such as aluminum. Some beta particles are capable of penetrating the skin and causing damage such as skin burns. However, as alpha emitters, beta emitters are most hazardous when they are inhaled or swallowed. Next slide. So radioisotopes used in nuclear batteries, the most common ones include tritium, which has a maximum decay energy of 19 kiloelectrons per volt, half-life of 12.3 years, and a specific power of 0.33 watts per gram. Carbon-14 is another beta particle. It has a maximum decay of 156 kiloelectrons per volt, a half-life of 5,730 years, but a specific power in watts per gram of only 0.0013. Nickel-63, another beta emitter, maximum decay 67 kiloelectrons per volt, 100-year half-life, and a specific power of 0.0058. Promethium-147, another beta, maximum decay 225, half-life 2.6 years, and a specific power of 0.41 watts per gram. Polonium-210, alpha particle, maximum decay 5,305 kiloelectrons per volt, half-life 0.38 years, and a specific power watts per gram of 141. And plutonium-238, another alpha particle, maximum decay energy 5593, half-life 87.7 years, and specific power in watts per gram of 0.56. Next slide. So tritium is produced in the atmosphere in small amounts by cosmic ray interactions with nitrogen, oxygen, and other nuclei, and it can also be obtained as a reactor byproduct. Sources such as neutron capture on deuterium in heavy water reactors. Next slide. Carbon-14 is a natural dominant cosmogenic production in the upper atmosphere when secondary thermal neutrons from cosmic rays are captured by atmospheric nitrogen. The carbon-14 is also generated anthropogenically. Extra C14 was added to the global inventory by open-air nuclear weapons testing in the mid-20th century. Next slide. Nickel-63 has an industrial production mainly by neutron irradiation of enriched nickel-62 in a reactor. An alternative route, fast neutron reactions on copper targets. Next slide. Promethium-147 is formed as one of the fission products of uranium-235 or plutonium-239 in reactor fuel. It's historically accumulated at processing sites such as the Hanford site, and minor routes neutron activation of suitable precursors is possible, but less commonly used industrially than straight fission product recovery. Next slide. Polonium it's produced industrially, typically by alpha particle irradiation of bismuth-209. A reactor route, neutron irradiation of bismuth-209 in reactors to form bismuth-210. Next slide. Plutonium-238 is a reactor target. It's produced by the neutron irradiation of neptunium-237. The neptunium-237 itself is recovered as a byproduct of irradiated uranium, natural or enriched during reprocessing, and then converted and fabricated into targets. Some legacy stock is historically came from power reactor fuel campaigns and special production reactors, but modern US production is essentially by the Neptunian-237 route. Next slide. Okay, so who invented the nuclear battery? Actually, it occurred quite a long time ago, more than 100 years ago. The inventor was a young man named Henry Moseley, who showed proof of concept in 1913. His nuclear battery consisted of a glass sphere silvered on the inside with a radium emitter mounted at the center of an isolated electrode. Electrons resulting from the beta decay of radium caused a potential difference between the silver film and the central electrode. However, the idle voltage of the device was way too high, tens of kilovolts, and the current was way too low for practical applications. So Moseley created the world's first atomic battery, or beta cell, while working in the laboratory of Ernest Rutherford. Moseley's career was cut short, however, when in August 1914, World War I broke out, and Moseley enlisted in the British Army's Royal Engineers. Moseley was serving as a technical communications officer at the Battle of Gallipoli when, on August 10th, 1915, he was shot in the head by a sniper. Moseley was only 27 years old when he died, and he is buried on Turkey's Gallipoli Peninsula. Next slide. So not a lot happened after Moseley's proof of concept for decades, but then in the 1950s, a couple of patents showed up. One of them was beta decay conversion into electricity, non-thermal, and the inventor was Paul Rappaport. And Paul Rappaport proposed the use of semiconducting materials to convert the energy of beta decay into electricity. Beta particles, electrons and positrons, emitted by a radioactive source, ionize atoms of a semiconductor, creating uncompensated charge carriers. In the presence of a static field of a p-n structure, the charges flow in one direction, resulting in an electric current. Batteries powered by beta decay came to be known as beta voltaics. The chief advantage of beta voltaic cells over galvanic cells is their longevity. Radioactive isotopes used in nuclear batteries have half-lives ranging from tens to hundreds of years, so their power output remains constant for a very long time. Unfortunately, the power density of beta voltaic cells is significantly lower than that of galvanic counterparts. Despite this, beta voltaics were used in the 1970s to power some cardiac pacemakers before being phased out by cheaper lithium-ion batteries. Next slide.
Janelle, we have a question from the audience.
Okay.
An audience member is wondering, what was Moseley's atomic battery used for at that time before World War I? Was this just a laboratory device, or did it have some sort of use?
It was just a laboratory discovery, a device. It had no commercial use or really even laboratory use. The unfortunate thing is that Professor or Dr. Moseley didn't have enough time. I mean, he just didn't live long enough to take it to the next level, which is one of the great misfortunes of history. But but he did show proof of concept. So there were two patents that appeared in the early 1950s. One was by Paul Rappaport, filed it for RCA. Interestingly enough, it was a German patent. But what he actually claimed was a primary voltage source in which the energy of nuclear radiation emanating from a radioactive material is directly converted into electrical energy by means of a semiconductor body containing a depletion layer, characterized in that the radioactive material is arranged in the space between several rod-shaped semiconductor bodies containing alternating p and n zones, and that every second depletion layer between these zones is electrically bridged. What's also interesting is that right around this time, a little bit earlier actually, Purdue University also claimed a nuclear battery. And this is a short and sweet claim, a device comprising a unitary body of germanium having a plurality of alternating regions of N-type and P-type characteristics and means connecting said regions in series, aiding relationship. So that's actually a really broad patent, but I don't know if they did much with it. Okay, next slide. Now, Bearden and Jordan early, as far as I can tell, uh, created the first thermogenic nuclear battery, and their patent application was issued in November of 1959. And what they claimed was a radioactive cell comprising an evacuated outer envelope, a thermally conducting capsule containing radioactive material characterized by emission of radiation selected from the group consisting of alpha particles, beta rays disposed there within, and a thermopile having two groups of alternating junctions and provided with a pair of output terminals forming the cell output, one group of junctions being in direct thermal contact with said capsule and electrically insulated therefrom, and the other group being in thermal contact with said envelope, whereby a temperature difference is maintained across said thermopile. Next slide. Okay. In the early days, the use of electrical or of nuclear batteries was for a particular medical device. In the 1970s, doctors in Paris implanted the first nuclear-powered pacemaker, and over the next 5 years, at least 1,400 additional people received devices, mostly in France and the United States. Encased in titanium, the batteries for these devices contained a radioactive isotope, typically about 1/10 of a gram of plutonium-238, and could operate for decades without maintenance. The invention provided relief to a population of people who previously needed surgery every few years to change out the pacemaker's chemical battery. Now, I looked for a few follow-up studies, medical studies, to determine whether there was any radiation harm that came to patients who had the implanted device with the nuclear battery, and I could not find anything. Clinically, the patients did very well with nuclear batteries. Next slide. Okay, but there were some problems with the use of nuclear batteries in the early days. As time went on, the whereabouts of radioactive pacemakers became increasingly difficult to track. In the United States, the devices were supposed to be returned to the US Department of Energy for plutonium recovery, but often that did not happen. Doctors changed jobs, manufacturers went out of business, patients died, and families forgot about their loved one's pacemaker. Too often, the radioactive material landed in crematoriums and coffins. Uncomfortable with the situation, the regulators worldwide stopped use of the devices. The last known nuclear-powered pacemaker was implanted in 1988. After that, aside from a few specialty uses such as deep space probes and Siberian lighthouses, development and deployment of nuclear batteries effectively came to a halt. Next slide. So this brings up the use of nuclear batteries in space, and this is an old use. This does date back to the 1970s. One of the most compelling applications, past and present, is an uncrewed spacecraft for long-distance missions, which require decades of reliable power. Now, solar power works for missions close to the sun, but by the time a spacecraft gets to Jupiter, the available solar irradiance drops below 4% of that on Earth. That leaves nuclear fission and radioisotope power as the only viable options for deep space missions. Fission is ideal for larger power needs in space, like NASA's proposed 100 kilowatt lunar nuclear reactor. But for lower onboard power needs, nuclear batteries offer simpler designs and lower mass. The current radioisotope workhorse in space is the radioisotope thermoelectric generator, or RTG, which produces a few hundred watts. By the late 1950s and early 1960s, US programs under the Systems for Nuclear Auxiliary Power umbrella developed RTGs for military and space applications, emphasizing reliability, long life, and containment in case of launch or re-entry accidents. Early RTGs carried relatively small radioisotope inventories and were originally designed to burn up on re-entry, though later designs were changed to fully contain the plutonium fuel in all credible accident scenarios. Next slide. Okay, NASA's two Voyager missions, which were launched in 1977, each carry 3 RTGs that weigh about 38 kilograms, including 4.5 kilograms of plutonium-238. They're cylindrical and about the size of an office wastebasket. And you can see one in the drawing, and it's in kind of the lower left-hand corner of that drawing, and it does look kind of like a wastebasket. They initially produced 157 watts of electric power, but that drops over time as the plutonium-238 decays. A 157-watt Voyager-based RTG that launched in 1977 will produce about 88 watts today. Another good use for nuclear batteries is to supply power in remote locations on Earth. Beginning in the 1970s, for example, the Soviet Union deployed over 1,000 RTGs in northwestern Russia to power its uncrewed lighthouses, radio beacons, and weather stations. Most of these batteries ran on strontium-90 and each weighed about 2,000 kilograms. The United States has deployed hundreds of similar systems for remote power, both on land and on the ocean floor, particularly for remote monitoring sites in the Arctic. Next slide. One new use where the benefits may outweigh the risks and costs is providing longer-lived power to soldiers, something the US military has explored. Soldiers' missions often take them to remote or unstable locations where electricity may be unavailable, preventing them from charging their equipment. This forces soldiers to carry batteries, the weight and life of which limit their missions. Small nuclear batteries would provide a lightweight alternative, potentially 1/100th of the weight, due to their higher energy density relative to that of chemical batteries. But they would need to be encased to shield soldiers from the radiation and designed to withstand harsh conditions, which would add weight. Another potential new use for nuclear batteries is to power autonomous sensors or robots that communicate, move, or fly. One compelling use would be insect-sized flying microdrones for civilian and military purposes, but collecting them at the end of their flights might be difficult and would also leave tiny bits of radioactive material littering the landscape. Next slide.
Janelle, another audience question.
Okay.
How are space nuclear batteries contained to protect the environment in case they re-enter planets like Earth? Do you have any details on how space batteries are made so that they can survive any accident scenario? I think was some of the wording you used.
Yes, I don't have the specific design changes that make that possible. But apparently they have been working on that. I could probably provide them after the meeting, but I don't have them right now.
Okay, fair enough.
So why haven't nuclear batteries been widely commercialized? One is obviously the safety and radiation risks. The primary safety issue involves the radioactive materials used, such as plutonium-238 or strontium-90, which can pose health risks through radiation exposure if mishandled, damaged, or accidentally released during events like spacecraft reentry. Environmental contamination from improper disposal or leaks is a major concern, potentially affecting soil, water, and ecosystems over long periods. Strict regulations and protective casings mitigate these risks, but public perception of nuclear technology often hinders acceptance. Production and cost barriers. Manufacturing nuclear batteries requires specialized facilities and materials, driving up costs significantly compared to conventional batteries. The process involves complex handling of radioactive isotopes, which demands rigorous safety protocols and limits scalability for mass production. Additionally, sourcing suitable isotopes can be challenging due to supply constraints and contamination issues with byproducts like other caesium isotopes in spent fuel. There are performance limitations. These batteries suffer from power density and conversion efficiency, typical outputting only microwatts to milliwatts, making them unsuitable for high power demands like consumer electronics or vehicles. Over time, radioactive decay leads to gradual power depletion, and the devices cannot be turned off, potentially causing unnecessary heat in applications. Technological hurdles such as improving beta particle conversion without radioactive damage to components further restrict their efficiency. And another problem are disposal and regulatory challenges. Spent nuclear batteries generate radioactive waste that requires secure long-term disposal to prevent proliferation risks or theft for malicious use. Limited data on environmental impacts complicates regulatory approvals and environmental impact assessments, while innovations like diamond-based designs aim to address some of the issues. Scalability and cost remain barriers for broader commercial viability. Next slide. Okay, and here's another barrier, and that is a cost comparison. The typical cost per kilowatt hour of a lithium ion battery is $85 to $151. For a nuclear battery, it's $300 to at least $500 for microwatts. The power output range for a lithium ion battery is watts to kilowatts, and it's nanowatts to microwatts for a nuclear battery. Applications, electronic vehicles, electronic storage for lithium battery, but only medical implants and clocks, and maybe a couple of other things for nuclear batteries. Next slide. So how are current nuclear batteries better than those of the 1970s and 80s? Modern designs such as beta voltaic batteries now use a broader range of radioisotopes and incorporate semiconductor materials that dramatically increase energy conversion efficiency. Some prototypes achieve over 8% efficiency compared to less than 1% in earlier models. This means less radioactive material is needed for the same output, reducing cost and risk. Recent nuclear batteries use advanced semiconductors such as titanium dioxide and silicon carbide and are sensitized with dyes or treated with citric acid to enhance electron collection and energy conversion. These improvements allow for much higher energy densities, sometimes 10 times that of a lithium ion battery, and longer lifespans. And some designs promise power for decades and even millennia. Modern nuclear batteries are designed to be much safer, with shielding that effectively blocks harmful radiation and materials that minimize leakage. Miniaturization is also advanced, enabling applications in medical implants, remote sensors, and space exploration, where size and reliability are critical. Modern beta voltaic cells offer extremely high energy density, but very low power density, typically in the microwatt to nanowatt range per device, even though they can deliver that power for decades. Commercial products such as the tritium-based nanotritium cells and other devices are explicitly positioned as long life micropower sources for sensors, medical implants, aerospace electronics, and other ultra-low power loads. Okay, next slide. Okay, I took a look at companies and university projects of interest in this nuclear battery area, just to kind of see what's out there, what's the big thing right now, and what's on the horizon. And the first company of interest is Beijing Betavolt. Next slide. Now, Beijing Betavolt, which in English would be Beijing Betavolt New Energy Tech Corporation, is a private Chinese startup. It announced plans last year to commercially launch a 1-watt battery in 2025. I could not get confirmation that that launch actually did occur. It may not have been able to obtain a license and funding to do so. I'm continuing to watch that situation to see whether they actually do have a commercial product. Assuming Beijing Betavolt's device has a conversion efficiency of about 5%, the battery would have to hold about 20 curies or 0.4 grams of nickel 63. This is well above the typical amount of nickel 63 available on the market, which normally is in the millicurie range. I was able to find 2 patents assigned to Beijing Betavolt, and this is where the story does get kind of interesting. These are Chinese patent applications. Their chances of being issued as patents are actually kind of small, according to Derwent. So we'll see what happens there. And they're not claiming anything outside of China. They haven't filed patent applications in any other countries. And I suspect this is due to an inability to obtain a foreign filing license. I think this is probably technology China would prefer to keep within China. Now, what's interesting about both of these Chinese patent applications, though, is that both of them claim priority from separate Russian patent applications. Next slide. So the first Chinese patent application, the 038, is a method for manufacturing a nuclear battery, characterizing that the method comprises multiple converters, which are fabricated on a diamond substrate using a specific process, obtain the open circuit voltage and short circuit voltage current of each of the plurality of converters. The plurality of converters are grouped to obtain at least two groups, each group including at least two converters connected in parallel. Converters in the same group are mounted in parallel on a substrate isolated from the substrates of other groups. Converters in multiple groups are mounted in a housing, and beta radiation source is mounted in the housing. Multiple groups are connected in series. Specifically, the ratio of the difference between the maximum and minimum open circuit voltages of the converters within each group to the minimum open circuit voltage of the converters within the group is less than the target ratio. The number of converters in each group is determined based on the fact that after the converters in each group are connected in parallel, the ratio of the differences in short circuit current of each group and the minimum short circuit current of multiple groups is less than the target ratio. Next slide. Okay, and this is the Russian priority case, which is actually quite a bit broader. The invention relates to a beta voltaic current source and a method for its manufacture. The BVCS contains a beta radiation source, a beta radiation converter, and an energy storage device. The source of beta radiation is placed on a converter. The beta radiation having a substrate made of a single crystal of diamond. The energy storage device is made in the form of a supercapacitor in which a non-woven material made of long carbon nanotubes is used as an electrode material, and a concentrated solution of sulfuric acid is used as an electrolyte. The method includes forming a beta radiation converter and placing a beta radiation source on top of it, forming an energy storage device in the form of a supercapacitor in which a non-woven material made of long carbon nanotubes is used as an electrode material. A concentrated solution of sulfuric acid is used as an electrolyte, and a source of beta radiation and an energy storage device are combined to form a BVCS. The effect, more compact dimensions of the BVCS and an increase in the output current of the BVCS in an extended operating temperature range. Next slide. Okay, now what's the plot kind of thickens here. The inventors for both of the Chinese patent applications owned by this Chinese company they're all Russian inventors. Next slide. And they're not just any Russians. These are rock stars in the area of nuclear batteries and the use of diamond in nuclear batteries. A research team led by Vladimir Blanc, the director of the Technological Institute for Super Hard and Novel Carbon Materials and chair of nanostructure physics and chemistry at the Moscow Institute of Physics and Tech, came up with a way of increasing the power density of a nuclear battery almost tenfold. The physicists developed and manufactured a beta voltaic battery using nickel-63 as the source of radiation and a Schottky barrier-based diamond diode for energy conversion. The prototype battery achieved an output power of about 1 microwatt, while the power density per cubic centimeter was 10 microwatts, which is enough for a modern artificial pacemaker. Nickel 63 has a half-life of 100 years, so the battery packs about 3,300 milliwatt hours of power per 1 gram, 10 times more than electrochemical cells. The nuclear battery prototype consisted of 200 diamond converters interlaid with nickel 63 and stable nickel foil layers. The amount of power generated by the converter depends upon the thickness of the nickel foil and the converter itself, because both affect how many beta particles are absorbed. Currently available prototypes of nuclear batteries are poorly optimized since they have excessive volume. If the beta radiation source is too thick, the electrons it emits cannot escape it. This effect is known as self-absorption. However, as the source is made thinner, the number of atoms undergoing beta decay per unit time is proportionally reduced. Similar reasoning applies to the thickness of the converter. Next slide. Okay, so a Schottky barrier-based diamond diode are rectifying devices in which the active semiconductor is diamond and the junction is formed between a metal and the diamond rather than a p-n junction, creating a Schottky barrier that controls current flow. Next slide. Okay, the Beijing beta volt nuclear batteries generate current through the semiconductor transition of beta particles, electrons emitted through the radioactive source, nickel-63. In order to do this, Beta Volt's team of scientists developed a single unique crystal diamond semiconductor with a thickness of only 10 microns. Next slide. So this work was done in Russia, and this is a schematic of their device from an article published in 2018, which made it prior art to the Chinese patent applications. But what you can see is the diamond cell and the nickel-63. What's kind of interesting is they are separated so that the nickel-63 does not actually contact the diamond cell. And that's going to be of interest in a second design that we're going to look at shortly. So the brain power came from Russia here, but the raw materials were going to come from China. That's why I think they created the Chinese company and filed the patent applications in China and are launching their product in China when that's where the market is. But that's also where the materials are that they're going to need to make this particular type of nuclear battery. So next slide. So the BV100 battery from Beijing Beta Volt costs about $300 to $500 per unit, which is much higher than conventional batteries like lithium ion or coin cells. For comparison, a standard lithium coin cell battery costs about $1.50 and lasts a few years, needing replacement every 1 to 3 years. Although the BV100's initial price is higher, it offers 50 years of operation without recharging replacement, which conventional batteries cannot match. In terms of energy density, the BV100 has over 10 times the energy density of typical lithium batteries, making it much more efficient in long-term energy storage, despite the high upfront cost. Conventional batteries typically need more frequent maintenance and replacements, adding to their lifetime costs. Thus, while the BV100s are more expensive initially, it could become cost-effective over time in applications requiring uninterrupted maintenance-free power for decades. The coin-sized BV100 outputs 100 microwatts or at 3 volts using nickel-63 decay and diamond semiconductors, targeting low-power uses like sensors, medical devices, and drones. It promises a 50-year lifespan without charging, extreme temperature tolerance, and safe operation with no external radiation. A 1-watt version is planned, potentially stackable for higher power. Next slide. Okay, now I included in the presentation several other Russian patent applications and patents naming the same group as inventors, just because it's kind of interesting. It'll give you more details in this about to be commercial product, and it is quite interesting. So this is one of them. It's a Russian having a patent having a priority of 2016. Next slide. Another one, it expires in 2026. Next slide. Another method for converting semiconductor converter, it expires 2037. Next slide. Next slide. Okay, and this is an article that may be of interest. It's again by the same Russian authors. High power density nuclear battery prototype based on the diamond Schottky diodes. And this explains in much greater detail. Next slide. Here's a structure of the Beijing beta volt stack. And you can see it follows the drawing pretty closely. Okay, next slide. Okay, the next place we're going to visit is the University of Bristol in England. And the University of Bristol has a startup to handle its nuclear battery work called Arconlight. So in 2016, a team of physicists and chemists from the University of Bristol made a diamond battery that used carbon-14 in the form of diamond-like carbon as a beta radiation source. Later prototypes found nickel-63 to be a better source with diamond non-electrolytes semiconductors for energy conversion. The Bristol group extracted carbon-14 isotopes from irradiated graphite from former nuclear power plants. Tom Scott and his colleagues incorporated this long-lived radioisotope into lab-grown diamond to generate current. In 2020, the Bristol researchers founded Arconlight to develop such a battery and unveiled the first ever carbon-14 diamond and diode devices in September 25th. Now their concept is different from the Russian group and Beijing Beta Volt in that Beijing Beta Volt stacked the nickel 63 isotope and the diamond into separate layers. Arconlight and the University of Bristol are actually implanting the nickel 63 within the lab-grown diamond. So they've been turning the irradiated graphite into diamond film, which itself is a wide band gap semiconductor. You've got diamond made from a beta emitter, which irradiates itself and creates electricity. Since carbon-14 has a half-life of 5,730 years, the batteries could provide intermittent power for thousands of years. In these extended lifetimes of nuclear batteries that make them particularly well-suited for applications like space exploration and long-term monitoring of infrastructure or challenging environments. Such applications could include deep sea exploration, space missions, and remote monitoring missions. Next slide. So Arconlight's battery products, Arconlight has sold a type of battery, but not yet the diamond-based nuclear battery that has received the most attention. The company has been selling a product called Beta Light Voltaic, which is a tritium-based battery used for sensor pods in the nuclear industry. This product is at high technology readiness and has been available in the marketplace for some time, providing up to 35 microwatts of power for low power applications. However, Arconlight's more advanced diamond-based nuclear batteries using carbon-14 or tritium embedded in synthetic diamond are still in the prototype or pilot scale production stage and have not yet been sold commercially as of late 2025. These batteries are being developed for ultra long life, maintenance-free power for sensors, LOT devices, and space applications, but are not yet integrated into major procurement programs or widely available for purchase. Next slide. So Arconlight and the University of Bristol have taken a different strategy from Beijing Beta Light and the other companies that we're going to be considering, in that they have actually filed in multiple countries. This is claim one of a US patent, but they also have patents in the European, the EPO, Canada, Japan, and Great Britain. The team of physicists and chemists from the University of Bristol have grown man-made diamond that, when placed in a radioactive field, is able to generate a small electric current. So it claims an electrical power source comprising a semiconductor, the semiconductor comprising a diamond material, and a radioactive source embedded within the diamond material, wherein the radioactive source comprises a beta-emitting radioisotope, and atoms of the radioisotope are substitutionally or interstitially integrated into the diamond material, wherein the diamond material comprises a plurality of regions in the form of layers within a continuous crystal lattice of the diamond material, and wherein at least one layer of the diamond material comprises the radioactive source, and at least one layer of the diamond material does not comprise the radioactive source. Next slide. Okay, the next company we're going to look at is City Labs. City Labs is a US company, and the radionuclide that it uses is tritium. And this company actually seems to be further along than the others that we've discussed so far, and that they actually have customers and commercial products. So the flagship offering is the P100 series nano tritium battery, which is a tritium-based beta voltaic battery designed for low power, long life applications such as sensors, microelectronics, and medical devices. The battery is currently available for commercial purchase with prices starting at around $5,250 per unit. And it's being used in fields like aerospace, defense, medical implants, and industrial monitoring. Pricing for different voltage models in the past ranged from $3,500 to $4,500, but the current base is $5,250. Next slide. City Labs focuses wholly on tritium, a radioisotope of hydrogen that emits beta particles. These beta voltaic devices act similarly to photovoltaics. However, instead of photons hitting a solar material, beta particles bombard a semiconductor and knock out electrons, creating electron-hole pairs. A charge difference builds up between the semiconductor's positive side with an excess of holes and its negative side with an excess of electrons. Next slide. Okay, its customers include Lockheed Martin and Northrop Grumman for aerospace and defense applications, such as durable power sources for equipment in extreme environments and secure crypto key retention systems. The United States Air Force and NASA for research and development projects, including powering satellites, probes, and advanced sensors. WellTech for downhole drilling technology, where the batteries are used to monitor wells in harsh conditions. Purdue University and NSWC Crane for collaborative research on improving battery performance for defense and aerospace. Medical device developers for applications such as pacemakers and other implants requiring long-lasting, maintenance-free power. Industrial and surveillance technology companies for sensors, RFID tags, and other devices needing reliable long-life power in remote or extreme environments. Next slide. Now, the patent portfolio of City Labs, which are all US patents, no other country, they all focus on increasing surface area to increase efficiency by absorbing more beta particles. So in this particular patent, what is claimed as a beta voltaic power source comprising a source of beta particles, a substrate with shaped features defined therein, an indium gallium phosphorus beta volt junction disposed between the source of beta particles and the substrate, and also having shaped features therein responsive to the shaped features of the substrate. The beta voltaic junction device for collecting the beta particles and for generating electron holes responsive thereto, and wherein the substrate comprises a gallium arsenic substrate having an orientation and surfaces of the shaped features having an orientation as shown. Okay, next slide. Okay, this is another City Labs patent. It's using a different technique, but for the same purpose. Next slide. Okay, and then next slide, same thing, next slide. Okay, the next company we're going to look at is Infinity Power. Now, Infinity Power has no commercial nuclear battery at this time, still in a prototype stage, and they don't have any patents that I could find, and I suspect it's because they're relying on trade secret protection, which may make sense under the circumstances. Infinity Power will use a nickel-63 ion radionuclide in its coin-size battery, but may need less of it because of the novel electrochemical conversion process it has developed. The company says its conversion efficiency exceeds 60%, about 6 times as efficient as the best radioisotope power generators. In Infinity's design, the isotope is dissolved or suspended in a proprietary liquid electrolyte. The decay of the radioisotope produces high energy beta particles that ionize the electrolyte, creating a potential difference between the anode and cathode immersed in the solution and driving electron flow through an external circuit to produce electricity. Next slide. Instead of using thermoelectric couples or a semiconductor junction, Infinity Power uses a specially designed electrochemical system in which the radiation drives redox reactions that separate charge and generate a usable electric current. Next slide. Okay, Ohio State University is actively working on developing a nuclear battery that converts nuclear waste, specifically gamma radiation, from isotopes like cesium-137 and cobalt-60 into electricity. This research involves a novel approach using scintillator crystals that emit light when exposed to radiation, combined with solar cells to convert that light into usable electric power. The team has successfully created a prototype small enough to power microelectronics, and this work is seen as a promising pathway to utilize radioactive waste for sustainable energy production. Next slide. Using a combination of scintillator crystals, high-density materials that emit light when they absorb radiation, and solar cells, the team, led by researchers from the Ohio State University, demonstrated that ambient gamma radiation could be harvested to produce a strong enough electric output to power microelectronics like microchips. Next slide. And the researcher behind all this was Raymond Kao. He is the lead researcher and showed that when cesium-137 was used, the battery generated 288 nanowatts, yet with much stronger isotope cobalt-60, the battery produced 1.5 microwatts of power, about enough to switch a tiny sensor. Next slide. And here is the patent from Ohio State. Next slide. And again, here's this is also from the patent from Ohio State. Next slide. Korea is also working on something. It looks like it might be similar to what the scientists at the University of Bristol are working on, but there's no indication that they're working together, although they might be. I couldn't find a lot on this, but it also looks like they're using a kind of a diamond-based technology. Next slide. The UK Atomic Energy Authority is partnering with the University of Bristol to work on a device using the diamond technology that they're developing. Next slide. And Suzhou University in China, now they're using a nuclear battery technology focusing on the use of americium as a radioactive source. The university's research team, led by Professor Xiao Wang, has developed a novel micronuclear battery that converts alpha radiation from americium into electricity with unprecedented efficiency, reportedly 8,000 times more efficient than previous designs. And here we would need more information to check out the veracity of that claim. Next slide. Again, this is a little more about Suzhou. Next slide. Next slide. Okay, and as a final matter, I took a look using Derwent at kind of a more global view of patenting in the area of nuclear batteries since 2008. And the number one patent holder in terms of countries, which unsurprisingly is China, with 9,921, EPO 394, Japan 2,094, Korea 1,169, other 566, Russian Federation 121, Taiwan 216, UK 136, the United States 1274, and WIPO 495. Next slide. Okay, looking at the top optimized assignees, other is the big one, which indicates, and there are a lot of small kind of one-offs where universities generally, sometimes companies, have a single patent or a tiny group of patents, but it involves, there are many, many inventors, and it's not really focused in any particular company or university. Although when you look at in those terms of entities, the largest holder is the Chinese Academy of Science with 425 patents, the State Grid Corp of China with 376, China Nuclear Power Design with 254, China General Nuclear Power with 219, LG Chem with 191, Toshiba 176, Sumitomo Metal Mining 148, Toyota 143, and Samsung 142. Next slide. And this shows the patent publishing trends since 2008. And there has been some upward trend. This is not an area of technology which is red hot, probably for the reasons mentioned during the course of this webinar. But it is an interesting area. Personally, I think there is a place for nuclear batteries in the technological world, but it's probably still going to be somewhat limited by the drawbacks of the radioisotopes themselves, as well as concerns mentioned, such as safety concerns. So that's about it for today. Thanks very much for listening. I really appreciate it. Thank you.
Janal, that was excellent. I have a few questions saved up for you from our audience. So let's see here. In your study of this technical area, did you learn anything about the potential for nuclear batteries that are powered by fusion power, or is that still a ways off?
No, a nuclear battery is always going to be it's always going to be powered by the release of the release products from a radioisotope.
Okay.
The energy and the particle release, the alpha and beta, or sometimes gamma particles.
So current nuclear fusion plants, or
That's
at least the plants, they're huge, right? I mean, they require a lot of power going into them.
They do, and I think that proof of concept has been shown. I mean, I think they've achieved their objective of having more power released than power inputted, but that is quite a different technology from nuclear batteries.
So if I'm designing a satellite and I'm trying to decide on my power source, what reasons would I have for choosing solar over nuclear? Are there other than distance from the sun? Is there a big price difference between, for example, is using solar cells in space cheaper than using nuclear batteries?
It might be cheaper, but this is where you have to look at the larger picture, the cost of launching, and all of the cost of all of the other materials on a satellite. Solar batteries might be preferable, especially if your goal is to stay pretty close to the sun. But if your goal is to go away from the sun, as was mentioned, you've lost most solar power by the time you get to Jupiter. So it's not going to work. You have to have another power source. But if you stay close to the sun, you're probably maybe okay.
Sure. What can you tell us about any international treaties that regulate or limit the use of nuclear batteries?
Yeah, I don't know of any, but there may be some.
Okay. All right. And I have one more complex question that I will email you after this is done. So that's all the questions I have.
Okay.
So thank you very much, Janal. That was a wonderful, very fascinating presentation. Thank you to the audience for attending. If you have any additional questions, please feel free to email me or Janal, and a link to the slides for today's presentation will be emailed to you. I hope you will tune in to additional episodes of the SLW Chemistry and Biology Seminar Series. Thank you very much for your attention today.
Thank you.